So today, this is the last lecture of this very short course about how to model, how to get some tools, analytical tools, to model the dynamic of opinion formation. So up to now, what we saw was more on the first day. We saw like more a physicist point of view to obtain some equations through a master equation. And still, we saw that we arrived at some maybe not that trivial partial differential equation, which describe the evolution time of some quantity, which allow us to understand the state of our system. And then yesterday we studied more deeply this kind of equations, but it was very elemental. But still, we end up with a nice wild-postness result with existence, uniqueness, continuity with respect to the initial condition. And just I mentioned at the end how to extend this kind of result to more complex equations, but very quickly. Okay, because still I must mention that there are a lot of work going on around this kind of equation, because they do appear not only in this in the modeling of opinion formation. This is one example. They appear though in biology. They appear anytime we want to model something that will be like a transport equation, or plus eventually some diffusive term. But I think it's important to understand the transport equation in itself. And so what I would like to do now was I would like to come back to the modeling phase of the first day, but with another tool, with approaching this kind of dynamic of information, but through a different approach, more based on which will remind us, for those who know about that, of that more the kinetical theory of gases, where with the Boltzmann equation and so on. So still we are still going around the fundamental ideas of statistical mechanics, but we will see them more from a mathematics side, right? And for that, I will be using mostly material based I found in this very nice book by Lorenzo Pareschi and Giuseppe Toscani. So I will just review a very basic. The plan is to review a very simple, very basic model and see what we can do, and then I guess we will do that for the first hour more. And then after a short break, maybe I would like to present you some more up-to-date research. I would like to present you this same model, but slightly more complex. Okay, and this is a paper of mine with Juan Pablo Pinasco and some other guy, but it's not for me. It's just to show you when you make things a little bit more complex, then it's not that trivial anymore. You already get some non-trivial difficulties, right? But still, you can use the same tools we saw yesterday, more or less, with some tricks in the middle I won't mention, but the spirit still will be the same globally, right? Because in the middle there are a lot of technical issues, but it's not very relevant here. And well, at the end, I will give you some precise references of, if you're interested, some books to look at, of people, interesting people, to check the web page and everything. Okay, so just if you want to go on in that direction to see a little more, but really, I think that at the end of today, you will have all the basic tools to understand a lot of paper, or at least what's going on in the paper. There are a lot of technical issues too, but well, that's unavoidable. So let's see a very simple model, which I guess it's probably the simplest one, really. But then from that very simple model, we can just make things more complex. And you will see later that when you do that, it's not that easy to analyze in that case, right? So, okay, so we take, as usual, we take a very large population of individuals, and each individual has an opinion. And now my opinion will be a continuous variable. I will call it W, general, and I will take it between -1 and 1. So I'm just thinking that, for instance, if you imagine a group of people discussing some subjects, for instance, are you in favor or against vaccination, let's say, which is quite a relevant subject by now. And W, having an opinion equal to 1 would mean that, yeah, you are very much in favor, right? And having an opinion equal to -1 would mean that, no, you are completely against vaccination, completely negative. Okay? And if you are neutral, yeah, your opinion will be around 0. And you imagine that all the number in between -1 and 1 could represent all the variation of opinion. Yes, well, I'm a little bit in favor, but not that much. I'm a little bit against, but not that much. All the subtlety. Okay, so just remark that this is different from the setting of the first day, because in the first day we only have 2 opinions, 1 and -1. Like if we are to choose between in favor or against, without much subtlety. Here, it's a little more complex. Then the dynamic still will be the same. We'll pick at random 2 agents with opinion W and W star, and we'll make these 2 agents interact. And due to this interaction, my 2 agents will change slightly their opinion. Okay, and I will have to specify how they will change their opinion. And here I will have a lot of freedom. I can put whatever I want. Okay? But the problem later would be to see how this microscopic rule of interaction I will put between my agents this rule will produce eventually some macroscopic effect. What kind of effect? And if we can prove that, if we can see that with simulations, and then if we can prove that using mathematics, right? But we have a lot of freedom here. Okay, so for instance, one rule I will choose is a rule modeling the tendency to compromise. The fact that it's a very well documented fact that when you are discussing with someone, usually you are making an effort to avoid confrontation and to just slightly move your opinion towards the opinion of the other guy, just to avoid open confrontation. So obviously, this is a very crude simplification of reality. Sometimes you are completely repelled by the other person and you go completely opposite to this other person. And you can model that too, right? Or you can make a mix between tendency to compromise with people, for instance, that are already thinking more or less like you, and with people that are thinking completely opposite from you, that then you can get repelled by them, right? Because if I'm pro-vaccine and I'm discussing with an anti-vaccine, maybe I will go more extreme about my pro-vaccine opinion, right? Or maybe not. Maybe the other guy will try to convince me slightly, and I will be slightly less pro-vaccine than before. But here, this is the freedom I have to choose the interaction rule. The thing is that usually you try to make something that makes sense, right? Okay, and then you do that. So this is my interaction rule. The opinion after the interaction, the new opinion, I will denote them by prime here. So W prime is the opinion of the guy after the interaction when the guy had before the interaction opinion W. Right? And the other guy who had at the beginning, at first, had opinion W star will have opinion W star prime after the interaction. And you see that this interaction here means that my new opinion W prime will be my previous opinion W, plus I will move slightly in the direction of the other guy. And how fast I will move towards the other guy, this is this coefficient gamma who models it, right? And this gamma will be important later because we'll do something with this gamma, which will allow us to simplify greatly. Right? So this is one rule, right? And then you repeat that a lot of time. Just when these two guys just end up the interaction, you pick two other guys, make them interact, and so on and so on and so on, and just hope to you wait to see if something happens at the level of the population. So there is a thing here that remark that every time I choose two agents to interact. And for what I saw some maybe 1 or 2 years ago, physicists started to investigate what happened when you don't not only two people can interact. Maybe there are 3 or 4 or 5, maybe a group, or maybe it's random, and it seems to change a lot of things. And the other thing here is that I'm assuming that the networks of relationships between all my agents in the population is a complete graph, meaning that anybody can interact with anybody, which is not obviously which is not realistic. It would be much better to put a real network there, but then it might happen that the topology of the network might have an impact on the dynamic. And so you usually study this with using simulations, but from a theoretical point of view, it's not that easy. But there are a lot of work going on around that in the probability community is doing a lot about random graph, and things are starting in that direction too, but it's not trivial, right? And maybe you can complicate things much fun. You can make things even more complex. Maybe you can put you can assume that your network of relationships is evolving at the same time that the social dynamic is evolving, and both of them are coupled. Maybe you interacted with someone and you didn't like that, so you cut a relationship with that guy. Or on the other hand, you reinforce this level of cooperation with the other guy. So maybe your network is dynamically evolving along with the dynamic, with the social dynamic. So you see, it's not that obvious at all. Okay, so that's why it's maybe the simplest model, because everything is simplified up to a very crude point. So just before showing you a simulation of that, very basic simulation, I did that. Just let me show you 2 videos about this tendency to compromise, this the pressure an individual can, a group can exert over an individual, and the pressure an individual, one single individual, can exert on another one just to convince him to do something really stupid. So there is a very classic experiment by sociologists in the 50s called Solomon Asch. So I will show you the experiment because it's quite funny for me. You can find it on YouTube. So I downloaded the video from YouTube, in fact. So let me show you that, and then I will show you another experiment, more recent, which is quite astonishing for me, because a girl is induced to do something completely pointless just because she's imitating others, because she don't want to stand alone. Okay, so let me show you these two videos just to convince you that tendency to compromise is not I don't put that only because it simplifies things a lot. So that's true, it simplifies things a lot, but not only that. It's this one. So just give me a minute that I need to make the video start. So share my screen. So I guess now you should see you should see the video. So it's a video from the 50s, okay? And the video is the following one. A lot of people, which are actors, are entering an elevator. And among them, there is one guy which is not an actor, which is the real subject of the experiment, which is a guinea pig. This is this guy in the middle, the one with the bold face. And see how all the people we are seeing them from the back. And these guys this guy is only, we are seeing his face, and he doesn't know what to do. So just see how he behaves. So he tries to stand against the group. He can't stand it, and he starts to switch, to slowly move around. Okay. Then after a short while, so same thing, same kind of setting. All the actors are entering, and this guy in the middle with the glasses is the subject, the guinea pig, right? And you see the pressure, the peer pressure, the pressure of the group. And there are a lot more like that. There is one with hat. Look at the guy with the hat in the middle. He is the subject. So you see, just he aligned with the other one. Okay, and look now. So just remember, the guy with the hat is a subject. All the other people are actors. And I remember there was something with a hat. Okay, so now all the actors are taking off the hat. They are putting their hat off. Their hat out. Yeah. Okay, so this was the first video. So sorry. Let me show you the other one, which is, so this one you can get it on YouTube. If you put Ash experiment or Ash peer pressure experiment, you will find. Okay, and this is the other video. Okay, so let me just explain you the setting. Just go back and okay. So the Asian girl here is a subject, right? All the other people in the room are actors, and they are in the waiting room of some medical facility, an hospital or something like that. And at some point, you will hear a beep, just a noise beep, something like that, which has no meaning at all. And when hearing the beep, all the actors will stand up and then sit down again with no reason. There is no reward, there is no sanction, there is nothing. They just hear the beep, stand up, and then sit down. Nothing else. But the Asian girl does not know that, because she was the last one to enter the room. And you will see how the Asian girl is adapting her behavior to follow the rest of the group. So just see what happens. So when you hear the beep, all the people stand up and then sit down. And you see the Asian girl, which is quite, she seems a little bit puzzled, because she does not understand why people are doing that, because it's a completely pointless behavior. But still, she doesn't want to stand out of the group. So she imitates everybody else. Okay. So now, from time to time, the actors will leave the room, one after the other, right? And still, the girls do stand up and sit down. So there is almost no pressure. She just incorporated the behavior. And now the girl is alone. And this is maybe the most interesting part, because the girl is alone. There is no more social pressure, nothing, but she will still go on, stand up, and sit down when hearing the beep. And now, new people, which are not actors, new random people from the street, will enter the waiting room. And these new people will see the Asian girl stand up and sit down. And there will be only two of them, the Asian girl, the new guy. And the Asian girl will communicate her behavior to the new guy. Just see that. So this is a new guy, a random guy, which he's not an actor. He's a real person. He doesn't know anything about the experiment. So you hear the beep, the Asian girl stand up, sit down, and the other guy do not understand why, obviously, because it's pointless behavior. And now see how the new guy will react. And now more and more people, new people, real people, not actors, will enter the room. And the Chinese girl, the Asian girl, will communicate the new behavior to all the newcomers. And on and on and on. So remember that all these people here, except the Asian girl, are real people, not actors. They do not know anything about the experiment. And so on and so on. So yeah, this is not very interesting. So yeah, this video, you can find it on YouTube, right? You put peer pressure experiments, something like that, you will get it. Just now, I will show you again. Let's go back to the slides here. So I hope that these two videos, may I convince you that, yeah, tendency to compromise, tendency to avoid confrontation, to not stand alone, the will to fit in, just really make that you want to imitate the other guy. You don't want you want to your opinion to get closer to the opinion of the other guy. So we have this dynamic, very simple. So let's see what happened with a simple simulation, right? It's easy to program, and it will give us a feeling. But remember that the main idea of the dynamic is that when two people interact, their opinions are getting closer to one another, right? So what may happen? Let's see that. Let's see that on a simple simulation I will show you now, and then we will see how we can analyze mathematically this kind of dynamics. So this is this one. So again, let me share my screen, which should be this one. So from the start, I just slightly there. Okay. So the initial condition is that I put a uniform distribution between more or less -0. So the opinion is initially distributed among my agents this way, right? So there is a piece of uniform distribution between -0.9 and -0.4. This is the left piece, and there is another piece of uniform distribution between 0 and 0.9, something like that. And then just repeat the dynamic, pick two guys at random, and make their opinion get closer to one another. And repeat. And you see that due to this tendency to compromise we put in the interaction rule, really the distribution of opinion is getting narrower and narrower, meaning that people are tending to share globally the same opinion. And if you wait a long time enough, you see some kind of accumulation of mass around one precise sorry that here. So maybe I should have make the simulation a little bit longer. But you see, mass is accumulating around some limit opinion, which would be more or less here. So this means that my distribution of opinion is converging to a direct mass, plus some random fluctuation because people are still interacting. But I would like very much to know if this is true first, if really my distribution of opinion is really converging to direct mass, and moreover, if I could find the mean value of this limit opinion, yeah, getting rid of the random, the noisy fluctuation around this limit opinion, right? So I want to do that, right? But now we know more or less what to expect. That is, we know that we should expect something like that. Okay. So, meaning that if we denote by ft the opinion distribution at time t is just check that ft is a probability measure on my opinion space, which is only the interval from -1 to 1. It seems that my ft is converging to some direct mass. At least I see that from the simulation. Okay, but now I want to prove that, and to prove that, it would be very nice to get some equation for ft, right? And from that equation, it would be nice if we could deduce that really ft is going to a direct mass. Okay? So this is more or less the path we took on the first day of the course, right? But we did it through the master equation and the weak formulation of the master equation. Now we will do that using another point of view, which is related to the kinetic theory of gases. So this is more or less the same idea as the Boltzmann equation, which describes the evolution in time of a density, the density of particle in a gas. So now my particle are my agent, my individuals, and I'm not interested in position velocity, but in the opinion. But the idea behind is more or less the same. So how can I get this equation for my opinion distribution ft? I will do that with a weak point of view. So I will just use a test function phi and look at that quantity. Okay. So this quantity is only you can think of it as the mean value of phi at time t over the whole population. For instance, if phi of w is w, that is phi is the identity, here I have the integral of w against my probability distribution. This is the mean opinion. I would be looking at the evolution in time of the mean opinion in the population. If I take for phi w square minus the mean opinion squared, I would have the variance of my probability distribution, and so on. Okay, so we think of phi as some macroscopic quantity we could observe the system, and I would like to know how this quantity evolves. And this is exactly what we did when we look at the weak formulation of the Maxwell equation on the first day, right? And here we can do more or less the same to obtain this equation in blue. So this equation is telling me that to see how the rate of change of this expected value of phi, what I have to do is I have to average, to take the mean over all the possible interaction I can imagine between two agents in the population. And for each interaction, I need to check how phi will change from the opinion at the beginning of the interaction and with respect to the opinion at the end of the interaction. And these two here means that I will pick at random in the population a guy with opinion W and a guy with opinion W star, which are the two people which are going to interact. So really, I'm taking the mean over all the possible interactions of all the possible jumps that can happen to phi between the new opinion after the interaction with respect to the old opinion before the interaction, right? So this is the meaning of this equation. And this is more or less the same idea as the Boltzmann equation, except that in the Boltzmann equation, on the left here, you have additionally, you have a transport term, because the particles of the gas are moving following the velocity. And on the right-hand side, you don't have exactly this expression. You have another kind of expression, which tells you how particles do collide. But the idea globally is the same. So right. So look at this kind of formulation. You can use it anytime you have interaction between two people, because the interaction in itself is hidden in the definition of W prime. W prime is this one. This is W prime, right? It depends on my opinion before the interaction and the opinion of the other guy before the interaction I will be interacting with. Okay, so everything is hidden within the W prime. So this equation is always a starting point. And everything happens when you look precisely at what is W prime. So obviously, this kind of equation has, if you are given an initial condition at 0, initial probability distribution of opinion over -1, then you get a unique solution to this equation. This is, you do that, you can do that in two ways, right? One way is very classical, very classical, which is based on Banach fixed point theorem. You rewrite your equation in that way. Here, you just introduce a new notation to handle easily the right hand side, which is this one here. Okay, so that when you rewrite everything, you get this. So you can rewrite your equation as a fixed point equation, which is this one. This means that f at time, my probability distribution at time t is my initial probability distribution plus the sum, let's say, of all the changes that can happen between time 0 and time t, which are all hidden within this q here, this expression q, right? So you just need to make some fixed point argument in a good space and check that everything's okay. The only thing here is that with this argument, you won't get that your ft is, you will get a unique fixed point, but you won't get that your ft is non-negative. So you need an additional twist to get that. So I put it here if you want to check it later, but it's not very important. Really, it's very classical. It's not complicated at all. You can find it in the book by Cecchiniani. And I guess in a paper of mine from 2018, we put the details because we were learning all the techniques. So we put all the details just to be sure we understood everything. But it's not complicated. And there is a more recent approach by Alberto Bressan, which you can find in his lecture notes from 2005. You can find them on internet freely. And some of the stuff here were clarified in this paper. The paper was about a much more complicated problem, but in the appendix of this paper, they use Bressan approach and just maybe clean things a little bit more, right? Just to make it easier. And here the approach is more or less the same, except that you are looking at your equation as an ordinary differential equation, but in general in some Banach space with some initial condition which belong to some bounding convex closed subset. Here my Banach space would be the space of bounding measure with the total variation norm. Yeah, we saw the total variation norm yesterday, and I mentioned you that it makes the space of bounding measure complete. And what you're interested in is you want to stay within, not you don't want an arbitrary measure which could change sign, which may not have mass equal to 1. No, you want a probability measure. So the idea is to get starting from a probability measure, you want to solve, starting from something in S, you want to solve this ODE, but making sure that at any time you stay in S. So for that, Bressan gave a few conditions which were clarified in this paper by both these guys. Very nice paper. So you have a bunch of conditions. Some of them are regularity of the Q. The first one is causality, meaning that the collision, who happened at time t, depend only on what happened up to time t. It does not depend on the future, which it more or less should be. Okay. And the most interesting condition is this one, the subtangent condition. This is the name Bresson gave to this condition, which is here to ensure that, think of it as if you were doing like the very simple numerical scheme, the Euler scheme in numerical analysis, when you try to solve an ODE. When you discretize time, and when you pass from one time step to the next one, you take your position at your previous time plus a small increment time the derivative. And this is exactly the same idea here. But what you want to do is that when you're slightly moving in the direction of your derivative, you don't want to you want to stay very close to the set of probability measure, because you want to stay within the set of probability measure. Okay? This is your set of constraints. You want to stay very close to it. So this condition is here to ensure that, starting from an initial condition within S, set of probability measure for us, you will stay within S at any time. Okay. The other conditions are more like regularity issues. Okay. Just to be sure that your Euler scheme will converge to something. Okay, but this is not that complicated. The most important condition is this one. And it can be, this is a very nice approach which can be useful at some time. We used it in the paper we did 2 or 3 years ago, and it works well, and it's very easy to implement sometimes if you can check this condition, which is maybe the most problematic one. So just all this to say that that getting a solution to this equation, no big deal. You can do that. It's not a big issue. Now, what you want to do is really how can I want to say something about the asymptotic behavior of my solution ft as time goes to infinity. We saw in the simulation that we should converge to a direct mass, right? So where does it come from? And here we have total freedom for phi. Phi could be any bounding continuous function. So we can try what happened for the mean opinion, where phi is the identity. What happened for the variance? If we are lucky, we get some information. And here, since this is a very simple model, we are lucky. We will get everything. When we will make things a little bit more complex, this thing will fail completely. But now it works quite well. So let's take advantage of it. So back to our problem. And we take as a test function, we take this one. So we are looking, really, this expression here is the mean opinion. So you put this function here, and you remember that the definition of W prime, the definition of what is your new opinion after the interaction. When you do that, you get W prime minus W, which was gamma time. Maybe I should have written this. Would have been better. This was this one. This was W star, the opinion of the other guy, minus W, minus my opinion. And when you put that into the integral, here you will get, so the gamma goes out. You will get the integral of W star against dft W star, just time the integral of dft W, but this is 1 because f is a probability measure, minus a symmetric term, which is so the same thing here, times the integral of dft w star, which is again 1. Okay. So these two integrals are the same, they cancel out. So you see that the derivative of the mean opinion is 0, meaning that your mean opinion is conserved, which is pretty good, because if we think that the limit will be a direct mass, as suggested by the simulation, then this direct mass should be located at this point. So this means that if really ft is converging to direct mass, meaning that all the individuals in my population are tend to share the same opinion, this common limit opinion should be M0, should be the initial mean opinion. So we solved part of the problem. We still have to prove that really ft is going to direct mass. So it would be good to look at the variance of ft, because if the variance, the spread of ft is going to 0, this means that ft is getting narrower and narrower, and at the same time the mean opinion is its mean value is conserved, so it's getting narrower and narrower around this mean opinion M0, and we are done. So let's try that. Let's try what happened when we put the variance. So we make the same kind of calculation. We just choose this step function. We put it here. So we'll get w prime minus w squared. We replace w prime minus w by its definition in this dynamic, gamma times w star minus w. Make some computation, and we are lucky because we find a closed equation for the variance, which is this one. But really, it's very rare to be able to do that exactly. Okay? Here it works because it's a very simple model. It's more like a toy model, a very pedagogical model, right?
Professor Saintier, your microphone.
I'm sorry. Oh, since then you...
No, it's only a few seconds.
Okay. I didn't realize. Sorry. So, yeah, we were just checking the variance. We are lucky enough, because the model is very simple, to get a closed equation for the variance. We solve it, and we find that the variance is going to 0 exponentially fast, which is pretty good, right? So that's good, because the spread of the ft is going to 0. The mean value of ft is conserved, so we are done. This proves that ft really is going to direct mass, and we know which direct mass. So maybe we could make just one more twist to this here. We could rewrite that really as a distance between ft and its limits. And yesterday we saw that a good distance for studying a transport equation was W1. Here, with the variance, W2 is more suitable. So just let me remind you this kind of definition, because later I will use this. So just yesterday I just put the definition of the distance W1, one definition, which is not the which is equivalent to the definition I'm putting here. So the Marshall-Ridge distances, there are a lot of them. Okay, there are the WP for p greater than 1, and you can even take p equal to plus infinity, but there are some, you have to be more careful in that case. And these distances comes from optimal transport theory, and they are defined in this way. So you can do that on any Polish space, which is a complete separable metric space. So you got a distance, and you are looking at some kind of average distance between any pair of points to the power p, except that your average, you are thinking it not over everything, not over anything. You are thinking it over any probability on the product space having marginals mu and nu, the two distances you are comparing. Okay, so this only means the marginal thing is not complicated at all. It just means that let me make you just a simple drawing to understand it, because it's no big deal. Let's say here is your product space x, and imagine here is your pi, your measure on the product, and what you do is you project pi on the first space of the product. So this gives you some measure here, which should be mu. And if you project pi towards the second factor of the product, you will get another measure, something like that, which is nu. Okay, this is the only thing about marginal. There is another. You can see that from integrated function, but it's not. I won't use it, so that's why I only put the definition for you to have it. But I won't use really the definition. Okay. But not that much. Okay, so and I was saying that this kind of distances comes from optimal transportation theory. When you think of mu and nu as two piles of sands of some material, and you want to transport one pile up to the other one, but maybe one measure is a pile of sands and the other measure is like a hole in the ground, and you want to fill the hole with a pile of sand, but transporting the sand is not free. There is a cost to do that. In that case, the cost is this one. If you want to move sand at x to a place y, you will pay this cost. So this is a total cost you will have to pay, right? In a very relaxed setting. Okay, but again, you can see all these details are in Cedric Villani's book, Topics in Optimal Transportation. Very nice. Okay, and the only thing I will care about is where nu is a direct mass, because in that case there is only one pi when nu is a direct mass, which is this one. In the drawing here, it's easy to be convinced about that, because imagine that my nu should be a direct mass here. So this is my nu is a direct mass here, right? My mu is okay. My mu is here. Then the only pi you can take is this one, which is a product of mu times the direct mass and x naught. Okay, and in that case, this expression here, my distance becomes this one. Right? So let's use that with p equal to 2, right? And we are in an interval, right? Not in a general metric space, right? So we use that. I put here some more properties of w pi. This is really a distance, which is not obvious. The triangle inequality is not obvious. You have to work a little bit. The convergence in that distance is the convergence against continuous function with at most, which grows at most like x to the power p. And with this distance, your set of measures, the measure satisfying this kind of condition, is complete. And when your space x with metric d is compact, then the space of measure is compact. So just a few properties, right? Just I mentioned them, but I won't use them that much. So let's go back to this expression here with p equal to 2. And with that, we will rewrite our variance. Because looks at, okay, so I will skip that. So I will just erase everything, right? So this is my variance, right? This is exactly the definition of the variance. This is, yep, this is the definition. The expected value of my random variable minus the expected value of the square of my random variable minus its mean value. And here the mean value is constant, it's m0. So this expression, you can rewrite it that way. And here you see this is exactly this distance. This is a pi we found earlier when one of the two measures is a direct mass, right? So this only means that the variance can be written as a distance, really. So our estimation of the variance, which decays exponentially fast, we can rewrite it as an estimate on the between the distance between my distribution of probability of opinion and its limits. So we've got everything. We've got convergence, the asymptotic behavior of the solution of our equation. We have the limit, precise limit, and we have a rate of convergence. But obviously everything works because we are working in just, I need to fetch something, just excuse me. But everything works because this model was really simple, really simple, and too simple, like maybe like too simple, right? Because the rules, the microscopic rule we used is very easy. Now, if we complicated things a little more, it won't be that easy. But in that case, we will use another technique, which is called, we will be taking the grazing limits in our equation here. So for the simple model here, this is not very useful to doing that because we already proved everything. But I want to introduce this technique now because it will be more transparent. And I will use it later on a more complex model, but without writing the proofs. Okay? But we'll see the proof, how it works here. And we will see it's very simple. It's a very simple idea, but which gives you a lot of information when you are not lucky enough to have closed equation for the mean value or the variance. So for instance, what's the idea? The idea would be to get from this integral differential equation I would like to get a standard PD, standard local equation. And the technique here is called grazing limits. It's a very standard technique in statistical mechanics, in the mathematical community. And here it's very simple. Just the only idea is to remember that in an interaction, this is my opinion before the interaction, this is my opinion after the interaction. And this is my change in the opinion due to the interaction. So assume that gamma is very small. Then in one interaction, my opinion will change, but very slightly, right? So I can approximate the jump of phi using a Taylor expansion easily in that way, right? Then I put that here and simplifies everything. Doing that, what do we get? Just forgot to write the detail here. So let's just check that. So imagine we take that expression and you replace it with that. What do we get? So there is a gamma going outside. There is a W star against, forgot to write that, against DFT W star time, there is what else? The integral of phi prime W minus, I will forget the gamma because it's only a constant. Okay, minus, and the other thing is W times phi prime, W times Z times nothing, times this integral of W star, which is 1. So the thing here is that here you recognize the mean opinion, right? So if you put things together, you will get exactly what I put here. Mean opinion times phi prime minus, this is the first term, minus the integral of W times phi prime. Okay? This is nothing else. Okay. Then we have to make some, just to clean things up, exactly as the first day, we have to make some time rescaling. Why is that? Because we are assuming that gamma is small, meaning that in one interaction, the change in opinion is very small. So if I want to see something at the level of the population, I will have to wait for lots of interactions to take place, because each interaction is producing a very slight effect. So I need to make to let happen a lot of interaction. And this is the meaning of this new time scale tau, because look that if when tau is equal to 1, okay, so in my new time scale, I just let pass 1 minute. This is as if in the order time scale, 1/gamma minutes passed. And gamma is very small, so 1/gamma is big, right? So I'm just saying that I let a lot of, I rescale time instead of thinking in, let's say, hour. I'm thinking I condense 1 hour in 1 second in my new time scale, right? Okay. So we got everything. And here you see that in that case, we end up with what? If there was no if this was an equality, we have here the weak formulation of the transport equation, right? Which will be this one. Yeah, dtf plus W my mean opinion minus W times F. Okay. And here, this is simple because my mean opinion is a conserved quantity. So here I got a constant. So this is pretty nice. But in case my mean opinion were not conserved, hey, this would not be that easy to study. And this will happen later. Okay, so I made all procedure here to approximate my original integral differential equation by a local equation, a transport equation of the same kind we studied yesterday. Right? So this is pretty good. And this can be justified, right? In the sense that really, if I denote by F gamma the solution of this equation, but now I want to keep track of the gamma because gamma is going to 0. Right? I make my time rescaling here. Then those G gamma will converge as gamma tends to 0 to a G in that space, which is the only weak solution to this equation. Okay, so this is pretty good, and this can be justified, and this is not very complex, right? Let's see how, just before going to the proof, why do I care about that? Because I know how I can solve this kind of equation, right? We saw that yesterday. To do that, you only have to follow the trajectories of the vector field. And what is a vector field? I got it here. This is my vector field, right? I only have to look at the sign of V because I'm in 1D. So the sign of V is telling me how the trajectories, how the particles are moving through V. And here this is easy because imagine you are here, -1, 1. You've got your mean opinion here. And how is your vector field? Well, if I'm above M0, then M0 minus W is negative. Okay. If W is below M0, then M0 minus W is positive. So you see that the vector field really is pushing everything toward M naught. So this means that really, if I got initially some distribution of mass, then everything which is on the right of M0 will be going to the left, and everything which is on the left of M0 will be going to the right. So at the end, everything will accumulating around M naught. And so we got back our direct mass. Right? Except that, I repeat, here, this was not necessary because we already have a closed equation for the variance and for the mean opinion. But later, when we'll study a little bit more complex model, we will not have that. And this procedure of grazing limit will be useful because it's much easier to analyze this kind of transport equation than the original integral differential equation, right? Okay, so this is pretty good. Now, just I mentioned a theorem, just stating that all the informal Taylor expansion we made can be justified. Okay, this would be good to, this would be nice to see that really it works. It's not just something informal, right? Really, you can prove that. Okay, so let's see a little bit what happens here. Okay, so just let me check time. Okay, so that's pretty good. Okay, we are good so far. Okay, so let's just see how it works. It's easy. It's very, very easy. It's easy because look at that. Those J gamma belong to this space, right? And I will restrict myself to a compact time interval. I cannot manage an infinite time interval. Yeah, this would be nice to get something, so to get some convergence holding for time going up to infinity. But so far, I can't do that, and I guess it's not that easy. But we need some compactness within this kind of space, okay? And continuous function going from a compact set to a complete set. It's not that hard to get some compactness. We have Arthur-Ascoli theorem, which is a very, very standard theorem, but very useful because it gives me compactness, and I need compactness because I want at least those J gamma to converge up to subsequence. And then, since I know that my limit equation has a unique solution, yeah, for a given initial condition, then I will get a convergence for any subsequence, so I will get the convergence of the full sequence of J gamma. So I just need to apply Arthur-Ascoli theorem. And this is a very powerful theorem because it gives me compactness, which is always nice. So Arthur-Ascoli theorem needs two things. First, sorry, if we fix a time, then we are looking at this sequence of priority measures, and we need this sequence to be pre-compact. And this is okay because since this interval -1, 1 is compact, then it's known that the set of priority measure over a compact set is compact. This is Prohorov theorem. Right? If you are not working over a compact set, but if you are working on R or RD, this is much more complicated to get compactness here because you have to add your sequence of measure must be tight, meaning that you shouldn't have any math going to infinity. Okay, so no mass escaping to infinity. This is tightness. But here we don't care because we are working on a compact set, which is a compact interval from -1 to 1. So this is good. Otherwise, it could be much tricky to get compact. But here it's okay. And then in Arthur-Ascoli theorem, we need some kind of uniform equicontinuity of our sequence of functions. here this means I will need something like that. If I got that, I'm done. Equicontinuity means that if if the time tau and tau prime are close to each other, never mind where they are precisely in this interval from 0 to t, then my two functions are close to each other. Right? Okay, so if I can have this kind of Lipschitz condition, I'm done. Okay. Clearly, I'm more than okay with that. And I need to have that for some distance, giving me the weak convergence of measure. It could be W1, could be W2, it could be a variance. Yeah. But if it gives me weak convergence, I'm good. Okay. Because once I've got that, then passing to the limits in the equation satisfied by J gamma won't be a trouble. So how could we get uniform continuity? Okay, so we come back to the equation satisfied by my initially satisfied by my f, and remember that I rescale time. Okay, so the new time scale is tau, but still it's easy to check that this new function in tau on the tau scale satisfies this equation. Okay. The only thing is that I put 1 over gamma here, which is the consequence of working on this tau time scale. Then we just do our Taylor expansion, but that time I keep track of the error term here, right? So yeah, so I've got the first part here is the one which will give me the final transport equation, and sorry, the error term here. Sorry for that. The error term here will give me this error term. And this is the one I need to control. Right? So this is not very complicated to control that, because remember that W and W prime are opinion. W and W prime belong to between -1 and 1. So I can bound that by 4. Right? Okay. And then, well, then I only have the second derivative of phi, of my test function phi. Okay, but the good thing is that this is bounded uniformly in time. This is pretty good, and it goes to 0 when gamma goes to 0. Bad thing is that there is this thing here, the second derivative of phi. So what do we have? We have, at the end, we have this kind of thing here. Then I take 2 times tau in tau prime, write this expression for tau and tau prime, and subtract them, right? And if I'm not mistaken, you can write, so you get something like that, something you will get from, let's say, tau prime. Here you will have a tau and a tau prime, okay? And the error term, you know how to control it. It gives you, well, I forgot the gamma. I put gamma less than 1. Okay, this is it here. And this thing here, you can control it by, that, right? Because M0 is between -1 and 1. So this thing here is less than 2, right? And I don't know why, and yeah, that's it. So this is very easy, okay? The only thing is that I need to introduce a new norm, which is very close to the W1 distance, right? Except that here, with the W1 distance, we are dealing only with Lipschitz function. This would be the fact that the derivative of phi is less than 1. But here I need to control the second derivative of phi. So this is like we are just smoothing Lipschitz function slightly, right? But you can prove that this gives you anyway, this norm gives you anyway a weak convergence on the set of probability measure, right? This is a paper, this is contained in a paper by Gabetta, Toscani, Weinberg. And so this is not that obvious, but this is not that complicated either. So what happened? The important fact is that we use this distance to measure the distance between these two measures here. And in that expression, we take the supremum of phi over phi. Yeah, for phi satisfying this bound. And we got this. So this is cool. This is exactly the uniform equicontinuity we were looking for. And just check, this was very easy to prove, right? So we are good. We have everything. We've got pre-compactness, uniform equicontinuity, so we can apply Arzel's-Police theorem. We are done. So we can this proves that the J gamma converge up to a subsequence to some J. J you can pass to the limits in here. Let's say in that expression here, you can easily pass to the limits, sending gamma to infinity because the error term here goes to 0. And you have weak convergence, so you can pass to the limit in that term without any trouble. And you get that the limits function J do satisfy this limit equation. And since this limit equation has a unique solution, you got the convergence of the whole sequence, not only a subset. So this is not complicated, but everything is justified, and it was quite easy, right? So what did we do up to now? We studied a very simple model, right? So simple that we could get conservation of the mean opinion, and very important, we could get a closed equation for the variance, which showed that the variance is going to 0, and we deduce from that the distribution of opinion is going to a direct mass located at the initial mean opinion. And we have an estimation of the rate of convergence. And another way to look at that problem, without using that we got a closed equation for the variance, is this Grazing limit, which consists in thinking that one interaction does not produce only a very slight modification of opinion. And with that trick, we can approximate the original integral differential equation by a local equation, transport equation. Just one more comment here. Imagine that in our microscopic interaction rule, imagine we had a noise. Could be, right? A noise which could be some random variable, right? So your opinion is getting slightly closer to the opinion of the other guy, but slightly perturbed, right? Or maybe you wake up in the morning and without interacting with anybody, you just slightly change your mind due to some random noise, right? Could happen. Okay, so what would be the influence of this noise on the equation? Well, this is not intuitively, this is not very complicated. Up to that point, no change. Change will happen when we do the grazing limits. So when we do the grazing limits, to take that noise into account, we will need to make a Taylor expansion up to the second order. So a second term will appear, which is a diffusive term usually, right? But it depends on the kind of noise you are putting in, right? And it depends on the balance between the strength of the noise with respect to the strength gamma of the transport term. It may happen that the noise is much more important than the transport term. So at the end, the transport term disappears and only the noise, the diffusive term, survive. Or on the other hand, it may happen that the transport term, the noise is so low, so it's not that intense, and it disappears. Or maybe the two term, transport term and diffusive term, balance as well, right? So in that case, you wouldn't get a transport equation like that, but you should have on the right hand side, you should have something like a diffusion. Diffusion. Something like Toscani did that, and you get a Laplace, something like Laplace. But maybe if you had some noise in the form of a Levy process, that is, a noise which from time to time makes some big jumps, maybe you get here a fractional diffusion. Okay, I say maybe because as far as I know, I don't know if someone already did that, right? But yeah, I think it could be nice to see that. Okay, right. And there is another approach to this kind of equation, which is much more based on heavy part. It's more probabilistic, because in that case you will have to keep track of the randomness of the interaction, and just really prove that as the number of individuals in your population is going to infinity, these random parts will go to zero. You can control it and it will go to zero. And this is not very complicated, but it's not that trivial, let's say. But it's not big deal. It's very well known since at least 10 or 15, I guess. Okay, just to have a big picture. Okay. Okay, so now, yeah, that's it. With a simple model, we are done. So let's move to something a little more challenging, right? So I would just talk about a paper I did a few years ago with Juanjo Pinasco, Maite Pérez-Llanos, and Analia Silva. And this is actually this is the first paper we did on this subject. And it's a very simple variant of this simple model, right? It's a simple variant because it's quite intuitively, it's quite natural. We are going to introduce some non-homogeneity among individuals, saying that all not individuals react the same way when they are interacting. So it seems very obvious, but it gave us an equation much more complicated to study. So just to end the course, let me show you this variant. Okay, so now in this variant, we think that an individual has an opinion as before, but he has two more parameters, which model how my individual will interact. First parameter is his persuasion capacity. How a good talker is I am. Okay, if my p is equal to 0, I have a probability of 0 to convince someone. Okay, because when I speak, no one listens to me. And when my p is equal to 1, then whenever I speak, I convince. That's it, with probability 1. Okay, and in between, well, there is some probability that the other guy will listen to me. And then there is another parameter, which is how do I react to the argument of the other guy, which would be my willingness to change opinion. This is my Q. If my Q is equal to 0, this means that there is no chance that I will change my opinion. So this means that whatever the other guy is telling me, I won't change my mind. Never. I'm a complete stubborn guy. For instance, I'm a complete anti-vaccine guy. So whatever I'm told, I won't change my mind. I always be an anti-vaccine because that's it. And on the other hand, if my Q is equal to 1, then if everybody talks to me, I will get convinced and I will change my mind as before. And the rule to change, the microscopic rule to change opinion is the same as before, except that now I have to incorporate these two parameters. If I have opinion W and I speak to someone with opinion W star, sorry, then this guy will convince me, but proportionally to what? Well, my willingness to change my mind, if I want to change my mind, because if my Q is equal to 0, this is 0 and my opinion won't change. And I have to take into account the power of persuasion of the other guy. How good a talker is it? Okay? And I will assume that these two parameters, P and Q, do not change in the dynamic, only the opinion. So you see, this is not a big change with respect to the simple model. Change their mind at any cost are the most important people. So here I represented on the x-axis is the opinion. Here is the opinion, W, between -1 and 1. And here is it's a Q value, willingness to change my yes. This is a Q value here, and the P value I put this relation because I just make the plot easy. And I just represent here the distribution of non-stubborn people in the population. That is, the people who accept to change their mind. There are non-stubborn people, but I didn't represent them because as time goes by, since they are stubborn, they never change their mind, but they do influence other people. Right? And so you see that initially my opinion was uniformly distributed. Okay, and you see that as time goes by, this distribution is moving and tends to align along some precise limit value, W infinity. And it would be very nice to find this precise limit opinion shared by all the non-stubborn people. And you see that they are not moving at the same rate, right? You see that the guy with a higher Q are moving faster. Those ones here, they are moving much faster than those here, which are moving much slower, which is quite obvious because Q is my willingness to change my mind. If my Q is small, yes, I will change my mind, but not that much. I'm quite reluctant. So at least the simulation shows something. It says me that it's saying me that the non-stubborn people do tend to change to share the same limit opinion at the end, and that the evolution of opinion depends on Q. But the thing is, it's the same question as before. How can I prove that? How can I prove that really they all share the same limit opinion? And it would be nice if I could find this precise limit opinion. And it turns out that this limit opinion will be completely determined by the non-stubborn people. And we will get an estimation of the rate of convergence. So how do we analyze that? We'll use exactly the same framework as before. We take a probability measure on the space of opinion P and Q with my two parameters. And I want an equation for FT. And from that equation, I would very much like to have some information, to deduce some information for concerning the asymptotic behavior of FT. So let's say the equation is the same as before, exactly the same, right? You can prove existence and uniqueness exactly as before, no big deal. But the thing now is that if you remember in the simple model, what we did was very basic. We look at the mean opinion and the variance. And we are lucky enough to see that the mean opinion is conserved and that the variance goes to 0. But now this computation failed, completely failed. And they fail because of the P and Q parameters. So that's it. We cannot do anything just looking at the mean opinions, the variance, nothing. So we will rely on the grazing limits procedure, thinking that we are going to send gamma to 0, thinking that one encounter just produces a very slight change of opinion. And see what happens, right? So how do we do that? Exactly the same as before. If gamma is very small, W prime, the opinion after the interaction, is very close to the opinion before the interaction, right? So their expansion. No big deal. Really, it's very easy. So we do that. I replace W prime minus W by its definition now. This is my dynamic, my microscopic interaction rule. And just rearrange a little bit everything, right? Just because it's quite messy. I need to recognize something, to understand something. So what happened here? Let's see. What do we have? We have these two integrals here. What is this one? This one is easy. I'm looking at the mean value of the p parameter in the population. But since p do not change in time, they are constant in time for each individual, this is a conserved quantity. This is fixed by the initial condition. Right? So I will give it notation. And what do I have here? Here this is like the mean opinion, but each opinion is weighted by the power of persuasion of the individual. So, which is quite obvious. This quantity should appear because it's not only the opinion of the guy which matters. It's only if this guy is able to communicate his opinion to convince me. So its power of persuasion is important. So it's quite, it's quite intuitively, it's quite obvious that the mean opinion times the power of persuasion should be meaningful, because it gives me really the weight of an opinion, how an opinion matters in the interaction, right? So these two quantities, I give them some notation here, okay, and the previous equation can be rewritten this way. Then there is one more change we could do, which is we could, this mean value of p, I will take it out. Okay, this is a constant, so I can put it out here, let's say, and just I will divide here by the mean value of p. Okay, and so this tells me that there is another quantity which could be important, which is this one, mt, which is almost as before. It's a mean opinion weighted by the power of persuasion, except that now the power of persuasion is not like normalized. Okay, this is really the quantity that matters, right? Because if I do that, what is my limit equation? This is my limit equation. Again, this is the weak formulation. Now, if here I had an inequality, this would be the weak formulation of a transport equation. But now the vector field of the transport equation is tricky. Okay, so let's see a little bit. So we do the time rescaling exactly as before, and we got our limit equation, right? Which should approximate the original integral differential equation. But the thing now is that the vector field of this limit equation is this one. And remember that MT depends on the distribution of opinion, because MT is this. It depends on the distribution of opinion. So we arrive at a transport equation where the vector field naturally depend on the distribution of opinion, right? If you remember yesterday, we saw another setting where this kind of equation appear when we were talking about taking a continuous limit in a system of ordinary differential equation, right? A big system of ordinary differential equation. So here we see another way of getting this kind of transport equation. But fortunately, yesterday we saw how to deal with this kind of equation, and we know that you have to trust me, but this vector field is not bad. It has good regularity property with respect to f and with respect to w. Good enough to have so that this equation is well posed. We have existence, uniqueness, continuity with respect to initial conditions. So we're good. So this is a more complex equation to study because it's nonlinear, but not that bad from well-posed point. And exactly as before, all this procedure of doing a Terra expansion, putting, approximating, and not everything can be justified exactly along the lines I showed you before. And it's almost slightly more complex, but almost anything. Essentially, I showed you everything before. Really, there are no lies. So this is a kind of theorem you can get, the same one as before. And then, yeah, then what do we do with that equation, right? Because, because the vector field is not easy. Okay. So what could we do? So maybe, let's say, for instance, if we knew by magic that MT is converging to some quantity M infinity. Assume we know that. What would happen? Yes, in that case, I would expect that in the long run, the solution of my equation is approximately the solution of this equation. And this equation is a common transport equation with a given vector field. And if you look at the sign of this vector field, it all points toward M infinity, right? Because if W is greater than M infinity, this is negative. So I go back to M infinity. If W, if my opinion is lower than M infinity, then this is positive. So my opinion is growing toward M infinity. So in that case, everything drives, the dynamic drives my distribution of opinion toward this M infinity. But the thing is that I don't know what is M infinity. It's only, for instance, for the moment, it's only a guess, right? And we will see that this M infinity will depend a lot on the stubborn individuals, the one who never change their mind. So just to set them apart, I will write my distribution of my initial distribution of opinion in two pieces. One piece for the stubborn individual and the other piece for the non-stubborn individual, right? And alpha is a number between 0 and 1, which is a proportion of stubborn individuals, right? And so for what we said here, we can think that in the limits when t goes to infinity, my distribution of opinion should go to what happens, the distribution within the stubborn population, which is fixed, constant in time, plus this thing, which is my limit opinion, M infinity, times the distribution of P and Q parameter within the non-stable population. But the big question here is, what is M infinity? And, well, how can I prove that, right? So let's see. How could we have a guess about the value of M infinity? Easy, but easy. Not that much, but it works well. So since everything depends on this MT, my weighted by the power of conviction, then I go back to MT. Okay, this is a definition of MT. And I will assume that I already have this convergence, hoping that I will get some equation for M infinity, which would give me the value of M infinity. And let's see. So I pass to the limit, MT goes to M infinity, and this piece here splits into two pieces, the one with the stubborn individual plus the one with the non-stubborn individual. Okay, because here at the end, this would be a direct mass for the opinion. This gives me the M infinity. And I've got this piece here, time P. This is the mean value of P within the non-stubborn population, right? Okay, so I have, so I got a nice equation, which is this one. And from this one, I got the value of M infinity. And what is this value? This is the mean opinion weighted by the power of conviction, exactly as before, except that everything is done within the stubborn population. So if all the guesses we made are correct, this will mean that in the end, in the long time, all the non-stubborn individuals tend to share the same opinion, and that common opinion is completely determined by the stubborn individual. Because the stubborn individuals are not influenced by anybody else, but they do constantly influence everybody else. So they drive, they attract towards them the rest of the population. And then well, all the stubborn individuals split the population between them. There is another thing I forgot to mention about this limit equation. Just if you remember the simulation, we were saying that the non-stubborn individuals were not moving at the same rate. Some were moving faster than the others. And the one moving faster was the one with higher Q, higher willingness to change their mind. And you see that here, this Q here, when Q is big, the change here is big. My vector field is big, so he's moving faster, my distribution of opinion. When Q is small, this is smaller, and everything moves slowly, right? So really, this kind of equation is very easy to interpret. It gives you a qualitative picture quite easily. So this is pretty good because up to now we have a nice guess for the limit of the distribution of opinion with what should be the correct value. And indeed, if you compute this quantity with the parameter of the simulation, it works well. Really, this M infinity is exactly what we observed in the simulation here. This is exactly the limit opinion we observed here. So it agrees too well to be pure chance. So this means that we are good. Maybe we are going in the right direction. But the thing is that still up to now there is no proof at all, only guesses. Okay. So how could we prove that? So let me show you a simpler step where we can prove everything easily. And then you will have to believe me that everything works well in the general case. So to simplify things a little bit, let us assume that in my whole population, there are only a finite number of distinct P and Q values. So I can divide my whole population, my whole non-student population, in according to their value for the P and Q parameter, and see within each subpopulation how is distributed the opinion. This is JI. Okay? And it's much easier because I got an equation for each JI, which is this one, which is almost the same as before, except that now, since in that subpopulation Q is equal to QI, I put QI here. But still, all these equations are coupled through MT, because MT is globally the mean opinion weighted by the power of persuasion in the whole population. Okay, so this is not to say I really have a system of equations, coupled system of equations. But the main point here is that if you remember the essence of the dynamic is that people tend to move. If I'm interacting with someone, I will move my opinion slightly towards the opinion of the other guy. So globally, my dynamic is attractive. And we can take advantage of that to prove that those JI, the spread of the JIs, their variance, is going to 0. This means that the JI are shrink. The distribution of the JI is shrinking toward a point. Maybe this point is moving. Okay, the JI maybe are shrinking and moving at the same time, right? But they're shrinking, and they're shrinking around their mean value. This is the mean opinion within the non-stable population with parameter pi and qi. So what is the good thing here? The good thing is that I only have to understand the dynamic of those mean opinions. And this is much better because we can write a linear system for those mean opinions. Something like that, with an explicit matrix A and an explicit vector B. So it's good because we passed from one coupled system of PDs to a linear system for the mean opinion. And it worked well because the dynamic, in essence, is attractive. If we change that, this probably won't work. And I guess it would be much harder. If we put some kind of repulsion between individuals, saying that no, you are thinking too different from me, you repel me, I'm getting away, or I will not interact with you. This is a bounding confidence model, meaning that if two guys have opinion too far away from each other, they do not talk to each other. Yeah, which could be meaningful because if you think left politically, maybe you won't read right-oriented paper, or you won't talk to right-oriented people. Right? And the behavior here of the system is much more, it's tricky. Okay, there are clusters of opinion forming, but it's very interesting. If you look at bounded confidence model on the internet, you will see there are a lot of papers about it. Okay, so going back to this, you have a linear system of equation, and it turns out that the eigenvalue of the matrix are all negative, are real negative forms. Okay, and you see here we have a bound on the real part of this eigenvalue, which depend on what? Which depend on the proportion of stubborn people. The more stubborn people you have, the more negative the eigenvalues, and so the faster the convergence. So this is to say that having stubborn people in the population help reaching a consensus in the population. And epsilon is inferior bound on the Q parameter for the non-stubborn individual. This means that all the non-stubborn individuals have at least epsilon of willingness to change their mind. And the higher epsilon, the easier they will change their mind, and so the fastest we have convergence. So this is pretty good because if the eigenvalues of A are negative, strictly negative, then yeah, this M will converge to something. And you can easily find the limit, which is this one. And it gives you exactly the M infinity we found earlier. So we're good. Because we are saying that these two are converging together. But these were very close to these. So at the end, the distribution of opinion within each subpopulation is going to M infinity. And we are done. We are done at least in that very simplified case, right? And in the general case, when you don't have necessarily a finite number of different values for P and Q, you have a distribution of P and Q values, you can more or less do the same thing, but it's a little more technical. And in particular, you will have to study the mean opinion within each subpopulation with a given value of P and Q, but this would be an infinite system of equations. Okay, but you can do something still, and this is the main result you obtain. But in a sense, this result we already have it when thinking that there are finite values for P and Q. The thing is that we cannot make any approximation argument here. We really have to work in one shot for an arbitrary distribution of P and Q. And the good thing is that we have an estimation of the rate of convergence, which is not that common. Okay, so I think not bad. Just checking time. So I guess it's time to conclude. So here I showed you today. I showed you a kinetic approach to opinion formation model, which can be applied to other settings. So I took opinion formation models the opinion dynamic as an excuse. Okay? You can use this kind of tool to model wealth distribution or a lot of other phenomena, pedestrian distribution, a lot of things, right? You can apply them to in game theory. You can to study, for instance, I'm studying auctions with a large number of players, and you can do something when you say that how players are behaving in the game, they do adapt their behavior according to their reward. If they are going well, yeah, they just enforce the strategy which gives them good reward. And if they are going poorly, they just lower their probability of playing that strategy. And you always end up usually with a transport equation, maybe with a diffusive term, and you have to study the vector field of the transport equation because it gives you a lot of information, at least qualitative. So just I had a slide of conclusions. Just give me 1 sec with some bibliographical references, just if you're interested. Just let me show you that. Conclusion here, you should see it. But just to show you some references, because I mentioned a few names during the lectures, and I didn't write properly the names, the name of the books, and so on. So I have to write. Okay, so we saw some tools, some of the tools. There's a lot more, but the thing I wanted to share with you was the idea that it's not a very complicated area to enter. You only need a few concepts, which are not very complicated, and you have a lot of freedom to do a lot of stuff. And it's quite interesting. There are a lot of activities around this kind of models, both in the physicist community and in the mathematics. I guess it's pretty interesting with a lot of possible application. And if you remember, for instance, what we saw yesterday about giving a continuous formulation of a system of bodies, this could be it can be very useful to deal with, for instance, a large population of neurons in brain, to have a continuous description of that. And it's already been done, of course, but the dynamic are non-trivial. Or if you think of machine learning, when you think of a deep neural network with a bunch of a lot of hidden layers, and each layer has a lot of cells, then maybe you can write some continuous equation for that. Okay, and I guess this was what I talked about that last week, maybe because last year sadly I couldn't attend the lecture, but there are already some work about that, some PD models of deep networks, and they use a kind of tools we saw yesterday, more or less. Okay, and so I wanted to show you this kind of references, which are very big references, right? On the physics side, there is a very nice survey by this. They are very highly cited physicists, and you have, for instance, this book about sociophysics, how to apply concepts from statistical mechanics to sociological issues. But it's a very physicist way of looking at things. But it's very interesting. It's worth the effort. And on the mathematics side, you have this book by Lorenzo Paolsky and Giuseppe Toscani, and you should check their webpage. They have a lot of very interesting papers, both theoretically, numerically, a lot of modeling stuff, and they are very active and it's very interesting. You can also check this girl. For instance, I remember she did a paper about modeling the ELO ranking system in chess, the game of chess. And if you are interested in transport equation for measure valued solution and issues related to measure spaces, you can check this very recent book, which one of the author was Piotr Gwazda, has a lot of trajectory in this topic, and it's very interesting. I forgot to mention you can check the web page of Jose Antonio Carrillo in Imperial College or Oxford College. I think it's in Oxford now. But it's aggressive. You can obviously check my webpage to see some work I've been doing about that in the last 5 years, mostly with my colleague from Argentina, Juan Pablo Pinasco, and a friend from United States, the University of Louisiana, Asmi Ackley. With ASME, it's more like a numerical scheme for transport equation for measure value solution, where you can add some, but usually with a motivation from the biology. So we had some coagulation term, fragmentation term. So I guess it's pretty interesting. Whereas with Juan Pablo, we are doing more like this kind of models applied to wealth distribution or game theory. It's very interesting to apply that to game theory, to deal with rational agents trying to learning how to play strategically so as to maximize their reward. And it's a pretty new area, I guess, which could be interesting. Okay, so thank you. Well, thank you very much. I guess